In this video, I'm going to show you a way that you can evaluate this definite integral of the square root function using Riemann sums. Now, normally in a calculus class, when you're using Riemann sums and you're using the definition to evaluate some integrals, you typically only use low-degree polynomials like constant functions, linear, quadratic, maybe cubic. But typically those are the only functions that are evaluated using the definition. Now, I have seen the square root function evaluated using the definition, but the thing about that is that every time I've seen it done, they've used the partition definition where you have subintervals that are not of the same width. And not everybody uses that definition in their classes, and not every textbook uses that definition. So a lot of books and a lot of teachers will just stick to the equal width subdivisions of the interval, and that's their definition. So in that case, you can't really use that approach to evaluate this integral. But what I came up with here was a way that you can evaluate the square root function using equal width subintervals. You have to be a little bit careful with it, but I was able to do it. So I wanted to show you this because I think if you're studying this and you only have this way of approaching integral, or if you're teaching and you only have gone over this approach, then you might be able to use this example as something that's a little bit more exotic than just the usual polynomial examples. So the idea behind this, there's one key idea, is that instead of taking the limit as n goes to infinity and letting, for each value of n, look at a subdivision into n subintervals, for each n, we're going to look at a subdivision into n squared subintervals. So for instance, when n is 2, we're going to have 4 subintervals. When n is 3, we're going to have 9 subintervals. When n is 5, there's going to be 25 subintervals. And those will be equal width. So what that means is our delta x is not going to be the length of the interval divided by n. It's actually going to be the length of the interval divided by n squared. Okay, so let me set up exactly how this is going to work. So we're going to start with the interval from 0 up to a. So a is just some positive real number here. And we're going to break this up into n squared subintervals. So that means our delta x is going to be the length of the interval, so a minus 0 over n squared, or an squared. We're going to use the right endpoints of each subinterval. So this first endpoint here is going to be a over n squared. The second one is going to be 2a over n squared, and so on. All the way down to the second to the last one would be n squared minus 1, a over n squared. And then, of course, the last one here is n squared a over n squared, which is just a. Okay, so we're using right endpoints. And so this means our sample points for the ith subinterval is going to be I times a over n squared. So IA over n squared. Okay, so that's the setup. Now let's see what the Riemann sum looks like. So we're going to take the limit as n goes to infinity. Now this is where it's a little bit different from how you normally approach this. So instead of taking the sum, so normally we would take the sum from I equals 1 to n, but since we're breaking it up for each n into n squared subintervals, we're going to go the sum from I equals 1 to n squared. And we're evaluating our function at the right endpoint, so that means the square root function evaluated at IA over n squared times delta x, which is a over n squared. Okay, so the only difference here is normally we would just go from I equals 1 to n. We'd evaluate the square root function at like IA over n, delta x would be a over n, but here we're doing it at n squared. So in a sense, we're letting the number of subintervals grow as the square of n instead of n. Okay, so let's simplify this and see what we get. So this is going to be the limit as n goes to infinity. So everything that has nothing to do with an I can take outside of the sum. So what can I take outside here? I can take this square root a, I can take the a underneath there, I can take that a. There's an n underneath, well, there's an n squared underneath the square root, so that's an n. There's another n squared. So altogether, it looks like there's a times square root a over n times n squared. So that's a to the 3/2 over n cubed. And what we're left with inside the sum, is just the square root of I. So we're going up to n squared square root of I. So this is the sum that we really have to look at, this sum from I equals 1 to n squared of square root of I. I can also take, since the a to the 3/2 has nothing to do with n, that can also come out. So let's go ahead and do that final one, and then we'll focus in on this sum here. So a to the 3/2 times the limit as n goes to infinity of 1 over n cubed sum I equals 1 to n squared of square root of I. Now, how are we going to get a hold of this square root of I sum? Because normally this is not one of the formulas that you have. You know how to add up the powers of I if they're non-negative integer powers. You can add up I squared, I cubed. And there's formulas for that. But this is square root of I. So we have to do something a little bit different here. What we're going to do is get bounds on this by basically either rounding up or rounding down to the nearest integer. So let's go ahead and do that. All right, so let me write out exactly what the terms here are, because this is going to be helpful. We're looking at the sum square root I. So if I write out what these terms are, it's square root 1 plus square root 2, root 3, root 4. Okay, I'm going to write out several terms here just to make it super clear what's going on. And then now let's go all the way up to square root of n squared. Okay, so there's two ways I can kind of bound this. One of the ways is I could replace this with numbers that are bigger. So I'm going to say this is less than something. So square root 1, that's just 1. But now square root 2, I'm going to round that up to 2. So in fact, all the three of them from square root 2, square root 3, square root 4, those three round up to 2. So 2 plus 2 plus 2. All of square root 5, square root 6, square root 7, square root 8, square root 9, so everything between 2 and 3, those all round up to 3. So that's 5 terms. 3 plus 3 plus 3 plus 3 plus 3. So you can see I'm writing them just directly below which one I'm comparing it to. And so on. Now, you need to see kind of the pattern going on here. When is this going to end? Well, let's see, I've got 1, 2, 3. So the last one here, this is equal to n. The last term is equal to n. So I'm going to have some n's. N plus n plus n. And now it's just a matter of figuring out how many of these I have. So I have the 1, 1. I have a single term of 1. I have 3 terms of 2, 5 terms of 3. And so the pattern ends up being I add 2 more additional terms each time. Now, you can go ahead and actually prove the expression rigorously by taking the number of terms up to, for instance, how do we know that there's 5 threes? There's going to be 9 terms, subtract 4 terms. So it's the difference of consecutive squares. But you can also just notice the pattern here. So this is equal to, so what I'm going to do is now write this as a new sum. We're going to sum from j equals 1 up to n. J times, okay, so this first term of 1 is j. So in the second term, j is 2. Now I just need to multiply by how many terms there are. And you can see that it ends up being 2j plus 1. For instance, when j is 1, there's 1 term. When j is 2, there's 3 terms. When j is 3, there's 5 terms. I think I said 2j plus 1. It's going to be 2j minus 1. 1 term, 3 terms, 5 terms. So notice the number of terms is always twice the numbers you're adding up, subtract 1. Now that means when we get to the very end, where we're adding up all the n's, there's going to be 2n minus 1 terms there. And so this sum now represents 1 times 1 plus 2 times 3 plus 3 times 5, and so on, all the way up to n times 2n minus 1. But we can add this up because now we can use the formulas for the sum of powers. So this is twice the sum of the j squared powers minus the sum of the powers j. Okay, now I'm going to use the formulas, which, if you haven't seen these before, I'll just give them to you right here. So the sum of the squares up to n is equal to n times n plus 1 times 2n plus 1 all over 6. I'm not going to prove this here. I'm not going to go too much into it. This is a very standard sum. If you're doing Riemann sums in a calculus class, as you've almost certainly shown this formula, you can prove it by induction. So it's a fairly standard formula. And then we're going to subtract from this the sum of the j's, so the formula for this is also a standard formula. This is n plus 1 over 2. So now it's just a matter of just collecting everything and doing the algebra. What I'm going to do is, we need a common denominator of 6. So I'm going to leave the 6 on the bottom there, and I'm just going to put 6, 3 over 6. And I'm going to factor out, so what's in common here, instead of multiplying everything out and then trying to factor, there's an n plus 1 all over 6. Okay, and then I'm going to see what's left over. Okay, so there's n plus 1 all over 6. And if you look at this first term here, what's left? There's a 2, and there's the 2n plus 1. So that's going to be 4n plus 2. And then from here, there's just a minus 3. Subtract 3. So altogether, this is going to simplify to n plus 1, 4n minus 1, all over 6. So this is what we would call an upper bound. We've replaced all the terms with something bigger, so we know that the sum of these square root of i's can't be any bigger than this. What we need now is a lower bound, and we're going to do a very similar thing. We're going to replace the terms with integers, except we're just going to round down. So let's see what we get in that case. So let me kind of recopy the same thing here. Square root 1 plus square root 2. The only difference is this time I'm going to round down instead of up. Okay. So this, I'll leave it like here so you can compare the two. So this is going to be greater than. Okay, now I'm going to replace the first 3 terms. The first 3 terms are going to round down to 1. 1 plus 1 plus 1. So I'm rounding down. Then the next one, square root 4 up to square root of 8, those 5 are going to round down to 2. And so on. All the way up to, now this last term here is n, but it's the only term that rounds to n, because if you're a little bit less than that, it's going to round down to n minus 1. So I'm only going to go up to n minus 1. N minus 1 plus n minus 1, and so on. And actually, I'm just going to leave off that last term. Remember, I'm replacing it with something smaller, so I can replace it with 0. I can just ignore it. So really, I only have these things that are adding up a certain number of 1s, 2s, 3s, all the way up to n minus 1s. Now I need to figure out how many I have of these, so this is very similar to what we did before. Let's count how many terms. I got 3 terms here. I've got 5 terms here, and so on. And hopefully you can see in comparison to the last one, where it was twice the number minus 1. So for instance, for 2, we had 2 times 3. We had 2 times 2, which was 4. Minus 1 was 3 terms. Here we've got 2 times 2, which is 4 plus 1. So the number of terms is actually 2j plus 1 in this case. So we can set up a similar sum as before, but it's going to look a little bit different. So this sum will read as the sum from j equals 1, but now we're only going to go up to n minus 1, and we're adding j times 2j plus 1. So that's our lower bound. And again, we can break this up into 2 pieces, 2 times the sum of the j squareds here, plus the sum of j. Notice that we only go up to n minus 1 though. Okay, so what does this end up making? Let's see. This is going to give us, okay, so this is going to be 2 times, alright, so when I plug into the formula, I have to be a little bit careful here. This is supposed to be n times n plus 1 times 2n plus 1 over 6, but we're only going up to n minus 1. So it's going to be n minus 1, and then this plus 1, which would be n, and then this, twice this, plus 1. Now twice 2n minus 1, remember that that's 2n minus 2 plus 1, which would be 2n minus 1. And then I'm going to divide by 6. And then I'm going to add, and then adding up to n minus 1, I have to do the same thing, plug n minus 1 into n for the formula. I would get n minus 1 times n minus 1 plus 1, which is just n all over 2. And again, a little bit of algebra, very similar to what we did before, get a common denominator here. I'm going to factor out this time n minus 1 over 6. And what's left over, n minus 1 over 6, is now, there's the 2n minus 1, so that's 4n minus 2. And then from here, there's plus 3. So it's a very similar sum, but not exactly the same. It's n minus 1, 4n plus 1, all over 6. So let's take a look at these 2 bounds here. Let me put little rectangles around them. Okay, so we have to remember where we were. We were looking at this sum up here. So what we've shown is that this sum is between these 2 expressions that we just got here. But what we're really interested in, if you go back here, is that sum times 1 over n cubed. So we really want to have it divided by n cubed. So let's go ahead and think about the inequalities we get now if we divide by n cubed. What we've really shown then is the following. I have just enough room to put this here at the bottom. So we've shown that n, so we've shown that n minus 1, 4n plus 1, all over 6n cubed, because I'm going to divide it by n cubed, is less than 1 over n cubed times this sum, which is less than the other sum we have up there, n plus 1, 4n minus 1, all over 6n cubed. But look at the outside expressions now. Since I've divided through by n cubed, what I've got is a rational expression of the same degree on top. The leading term is 4n cubed on top of each of those, and the 6n cubed on the bottom. So by some standard facts that if you're doing any kind of Riemann sum problems here, you know this, it's the ratio of the leading coefficients. So that means that this expression over here, as n goes to infinity, this is actually going to 2/3, and this is going to 2/3. So by squeeze theorem, so just like the ordinary squeeze theorem for functions, if you trap a sequence in between 2 other sequences going to the same limit, this has to go to 2/3 as well. So that we've shown that. And now we can go back up here and we can finally finish this off all the way back up at the beginning because we've calculated this limit now is equal to 2/3. So we get, which of course is the value of the integral, 2/3 a to the 3/2. So if you like this video, please like, share, subscribe, and I'll talk to you later.